Welcome to the Naval Film City banauli movie developers or banauli, and I am Fake Einstein from Germany, and today I am going to discuss about the statement of or postulates of a special theory of relativity given by original Einstein in 1905. So before knowing this postulate, let's once again see the definition of inertial frame. So an inertial frame is one in which a body at rest and not under the influence of any force remains at rest. Now let's see the postulates of a special theory of relativity given by original Einstein. First postulate: the law of physics has the same form in all inertial frames of reference moving with a constant velocity with respect to each one another. This postulate represents the absence of a universal frame of reference. If the laws of physics had different forms for observers in different reference frame in relative motion, it could be determined from these differences which objects are stationary in space and which are moving. But because there is no universal frame of reference, this distinction between objects cannot be made. For example, if we are in a free spacecraft in a space from which we cannot see anything except another spacecraft which is changing its position relative to us, we cannot say which balloon is really moving. Now the second postulates: the speed of light in free space has the same value for all observers in different inertial frames of reference. And this postulate follows directly from the result of the Michelson-Morley experiment. Next, now the Fake Lorentz will teach you about the Lorentz transformation. So go to the Fake Lorentz. Hello, welcome to the fashionable film city banauli. I am Fake Lorentz, and now I will discuss about the Lorentz transformation given by original Lorentz. So before to know about the Lorentz transformation, first see the Galilean transformation. So here you will learn the Galilean transformation. Here we see two frames m and m dash, and m dash is moving with velocity v in x direction. Consider x, y, z, t be the space and time coordinates of an event for an observer on the frame in m frame, and x dash, y, z dash, t dash the coordinate of the same event seen from the observer on the frame m dash. Let the time be counted from the instant when origin O and O dash of these two frames momentarily coincide. We have to see how are the measurements x, y, z, t related to x dash, y dash, z dash, t. According to the classical mechanics, the measurement in the x direction made in m dash will be smaller than that made in m by the amount v into t, which is the distance moved by m dash in the x direction. So we can write x dash equals to x minus vt, which is equation 1, and since there is no relative motion in the y and z direction, so we can write y dash equals to y and z dash equals to z, given by equation 2 and 3. In classical mechanics, the time interval measured in different frame of reference in relative motions are the same, and so we can write t equals to t dash. This is equation 4. Now the set of equation 1 to 4 are the Galilean-Newtonian transformation equations. They, however, violate both of the postulates of a special theory of relativity. The equations of electromagnetism assume very different forms when these equations are used to convert quantities measured in one frame with the equivalent quantities in the another frame. This violates the first postulate of a special theory of relativity. Again, if we measure the speed of light moving along the x direction in the frame M to be c, that in the frame M dash it will be c dash equals to c minus b, and this violates the second postulate. Now we will discuss about the Lorentz transformation equation given by original Lorentz. Let us now talk the set of transformation equation directly from the postulates of a special theory of relativity. We can reasonably assume that a measurement in the x direction made in frame M is proportional to that made in frame S dash. That is, we may write x dash equals to gamma open braces x minus vt close braces equation 5. So according to the first postulate, the equation, that is laws of physics, must have the same form in both frame M and M dash. Therefore the corresponding equation of x in terms of x dash and t dash will be the same form as given in equation 5, except that v will be replaced by minus v. Thus we can write x equals to gamma open braces x dash plus v into t dash close braces equation 6. The time coordinate t and t dash, however, not equal. Let us now substitute the value of x dash from equation 5 in equation 6, and we get a relation x equals to gamma open braces x minus v into t close braces plus v into t dash close bracket, or x by gamma equals to gamma x minus gamma into v into t plus gamma into vt dash. Hence we get t dash equals to gamma by x by gamma into v minus gamma x by v plus gamma into t equals to gamma into t minus gamma x by v open braces 1 minus 1 by gamma square close braces. This is represented by equation 7, that is t dash equals to gamma into t minus gamma x by v open braces 1 minus 1 by gamma square close braces. And similarly we can write the time in the frame M t equals to gamma into t dash plus x gamma x dash by v open braces 1 minus 1 by gamma square close braces. This is represented by equation 8. Now gamma can be evaluated from the second postulate of a special theory of relativity. Suppose a light signal is given at the origin at time t equals to 0 and t dash equals to 0, that is when O and O dash coincide with each other. The signal travels with a speed c, which is same for both the frame according to second postulate of relativity. Its position as seen from m and m dash after some time is given by x equals to ct and x dash equal to c into t dash. X equal to ct and x equal to c into t dash. So using these values in equation 5 and 6 we get ct dash equals to gamma into t open braces c minus v close braces, this is equation A, and ct equals to gamma into t dash open braces c plus v close braces, this is equation B. Now from a t dash can be written as t dash equals to gamma into t by c open braces c minus v close braces, and using this in equation B, ct equals to gamma into t dash open braces c plus v close braces, that is ct equals to gamma into gamma t by c open braces c minus v close braces into open braces c plus v close braces equals to gamma square t by c open braces c square minus v square close braces. This implies c square t equals to gamma square t into open braces c square minus v square close braces. This implies gamma square equals to c square by c square minus v square, or gamma square equals to 1 by 1 minus v square by c square. So finally we get the value of gamma equals to 1 by under root 1 minus v square by c square. This is given by equation 9. So now using this value of gamma in equation 5 and 6 and solving, we get x dash equals to x minus vt divided by under root 1 minus v square by c square, and this is represented by equation 10, and x equals to x dash plus v into t dash divided by under root 1 minus v square by c square, and this is represented by equation 11. Again, using the value of gamma in equation 7 and 8, we get t dash equals to gamma into t minus gamma x by v into v square by c square equals to gamma open braces t minus x into v by c square close braces, or t dash equals to t minus x into v by c square divided by under root 1 minus v square by c square. This is equation 12. And similarly we can find t equals to t dash plus x into v by c square divided by under root 1 minus v square by c square. So this is the transformation relation for time in these both frames. In the general case, when the light signal is not restricted to travel along the x-axis alone, we get two more relations like y dash equals to y and z dash equal to z given by equation 14. since these distances are measured perpendicular to the velocity. Now, equation 10, 11 and 12 are known as Lorentz transformation equations. They are used for transformation of the space and time coordinate of an event from one frame of reference to into another in uniform relative motion. There are two important points for the Lorentz equations. First, the measurement of position and time depends upon the frame of reference of the observer. Two events which are simultaneous when viewed from one frame of reference are not simultaneous when viewed from a second frame which is moving relative to the first. Now the second point. The Lorentz equation reduced to the classical Galilean equation when V is very less than C. Therefore, the consequences of a special relativity are not apparent unless enormous velocities are involved. So here we learn about the Lorentz transformation and its consequences. So again you are visiting the banauli film city here, and with this I would like to end my lecture here, and next time I will give another lecture on these topics in banauli film city. So very nice to visiting this banauli film city.